In an earlier class, we were discussing about the valency controlled semiconductors, primarily the impurity effect in controlling the conductivity of some of the oxides, the non-stoichiometric oxide in particular. We have seen the conductivity is closely controlled or very strongly controlled by the non-stoichiometry, and that non-stoichiometry relates to the defect concentration. However, the defect concentration can be fixed by addition of impurities, and those are called valency controlled semiconductors, and we have given two examples of NiO, nickel oxide, and Fe2O3. I have also seen that the conductivity in such oxides decreases or increases quite significantly. In this case, the plots have been made for resistivity as a function of dopant concentration. So, in case of NiO, it is the lithium concentration. In case of Fe2O3, it is TiO2 concentration, which decreases the resistivity quite significantly. I also mentioned that these are independent of PO2 and also on temperature. So, there is a illustration here how the defect concentration changes as a function of temperature. As a function of temperature, of course, is 1 by T has been plotted as a defect concentration, and we will see Al is the impurity here. Al2O3 has been added to MO, the original host oxide is MO, and to that Al2O3 has been added, that means this is trivalent, this is divalent. So, this is a effectively positive charge of the defect concentration, and that remains constant. The defect concentration remains constant as a function of independent of temperature. So, these are the intrinsic region, of course, at a very high temperature. The concentration of the intrinsic defect, that is a vacancy or the metal remains constant, is controlled by this, and however, the oxygen vacancy changes at a lower temperature is much lower than the impurity concentration, but at a higher temperature it takes over, and therefore, the intrinsic defect concentration predominates over the impurity concentration. So, impurity concentration is controlled or remains constant over the temperature range. So, at lower temperature it predominates, whereas higher temperature intrinsic conductivity comes in. So, if you plot the log conductivity versus 1 by T, like in earlier other semiconductor, here also you have an extrinsic region and an intrinsic region, and the slope do change. This is the activation, there is no activation here, whereas there is activation energy for a higher temperature. So, this becomes the intrinsic region and this becomes an extrinsic region. Of course, it is only the concentration has been plotted here. If you plot log, the other term also will come in, that is the mobility term. So, mobility may change, and therefore, there will be a slight slope here. Well, having discussed all these mechanisms and the nature of different conductivities in different oxides, we have been referring that there is basically an electronic conduction, either the electrons or the hole conduction. So, either the electrons or the holes are the basic charge carriers here. Only difference, of course, compared to the elemental semiconductors or in metals. In metals or semiconductors, as we have mentioned earlier, that they are relatively more free, whereas in a oxide semiconductor, the charges are much more strongly attached to the ion cores, and therefore, the charge carrier here is really not a free hole or free electron, they are called polarons. Okay. We will see what is that polaron means, but before that what is the mechanism by which it actually moves, and this is a animated view of what exactly happens when an electron, because we have seen even in valency controlled semiconductors and so on, or any other semiconductors or transition metal oxides, the electrons are basically getting attached to one of the cations, and that is how the valency of that cation gets changed. A 2 plus, for example, if this charge carrier, which is basically a polaron or a form of quasi particle electron plus polarization, we could discuss it a little bit later. So, this is the charge carrier here. For the time being we consider it as an electron, okay, and that is sitting on the site of the M plus or the M 2 plus. So, in a lattice of M 2 plus and O 2 minus, you have an additional electron here which is sitting at the site of the M or the metal, and it changes the valency from 2 plus to 1 plus. So, that is what happens. Then this electron actually what they call hopping mechanism, it hops from one site, one metal site to the another, and then go to the another, then goes to the another in this manner. This is what has been animated here. Right. So, the electron goes there, it sits over on the top of another metal. In the process, this becomes M 2 plus and this becomes M 1, M plus, and then again it goes to another metal site and also makes the other one M plus, and then goes to another one, this becomes M 2 plus, this goes to becomes M plus, and in this way it goes on. Right. Finally, from this side it has moved through the lattice by a kind of hopping mechanism, and finally it has gone to the other end of the solid. So, this is what we call the schematic representation of hopping conduction. So, the electrons or the charge carriers in this case is actually moving from the lattice points to the lattice points. So, the resident time in between the lattice is very low, either it is residing very close to the one of the cationic sites, or it is moving into the through the material, and it is really not staying any place in between. So, that is known as the hopping mechanism, and then we come to the so called concept of polarons, because these are the tightly bound electrons, and these tightly bound electrons have a different characteristics other than the free electrons which we have in metals or elemental semiconductors. So, as per definition or as per understanding, a polaron is a quasi particle composed of a charge, which is an electronic charge, obviously either electronic charge or a whole charge or positive charge, together its polarization field. The electronic charge interacting with its surroundings, dielectric medium, because they are relatively less conducting, polarizes the same and carries this polarization field along with it. So, it is basically a combination of a charge along with its polarization field. So, interact because of the interaction of the phonons, there is a the electron characteristics or the characteristic of the free electron is slightly different. In fact, its effective mass is also different, and as if it has a larger size. Okay. So, it carries that polarization field along with this, and that is why it is called polaron. The concept is important to explain the conduction phenomena in materials in which the electrons are relatively more localized, that is what was mentioned. than the normal semiconductor, as for example oxides and organic semiconductors. So, if you want to understand the conduction mechanism or the charge transport mechanism in particularly the oxides, which are more ionic in character, and organic semiconductors which are more covalent in character, in those situations the concept of these polarons are more useful, and one has to understand how exactly the charge carriers. Of course, what I am talking about is more a simplified manner, simplistic manner. There are more complex theories to this. The long range interaction generates a region of permanent lattice polarization and deformation surrounding the electron, and the same is carried by the electron during its movement through the medium. Is more or less the same thing is being talked about. It is like a cloud of phonons accompanied by the electrons. So, now we are talking about a cloud of phonons, we are talking about cloud of electrons. So, the electron is a sea of phonons, that is called, they are sometimes called the sea of phonons, and that is the lattice vibration, and the cloud acts as a potential well that hinders the movement of the charge, decreasing its mobility. So, the mobility, obviously the mobility of the, because we have been talking primarily of the concentration of the defects, concentration of the charge carriers, that is certainly one of the important component which determines the conductivity or the resistivity. But in addition, there is another very important term is the mobility term. So, it is also the mobility which determines the overall conductivity, and the polarons because of their polarization associated with it, as if a much larger molecule, larger species is moving within the medium, and therefore, its mobility is much less, and it has different interrelations, different characteristics so far as the mobility is concerned. So, this is all about polarons. We will not go much more details into it. So, that really completes our discussion on the semiconductivity in oxides, how it is determined by the partial pressure, how it is determined by the impurity content, and how it is determined, to what extent it is determined by the temperature, and all these things can be explained once we understand the band diagram of the semiconducting or the insulating oxides. There is another very important phenomena in oxides, particularly when you are talking about conductivity, the electrical conductivity, and that is ionic conductivity. We have also seen that in a non-stoichiometric oxide, where the defect compensation is primarily because of by the ions or change of the concentration of the ionic defects, there we are not talking about the electronic charge carriers, either the negative charge carriers or the positive charge carriers, electrons or holes. Their conductivity is primarily controlled by the concentration of ions, and they give rise to so called ionic conductivity by a diffusion mechanism. So, that there is not only charge transport, but there is a mass transport as well, and both of them are interlinked. So, one has an interrelationship with the other. So, let us talk little bit about the ionic conductivity. The ionic conductivity, which arises from the mobility of the ions, is a very important property of a group of ionic compounds. Okay. In fact, there are many technological applications or industrial applications for these ionic conductors. Since most of these oxides are of course solids, so and ionic conductivity is one of the major requirement of a electrochemical system, electrolyte of an electrochemical system. So, these oxides or these compounds are also known as solid electrolytes. So, the electrolytes in the solid state, and one can make electrochemical cells out of it, and that cells have a tremendous importance in particularly in the current context of energy crisis and the energy technology. So, We will discuss them at a later stage, but now for the time being let us try to understand what is this ionic conductivity and what is its characteristics. As I mentioned, the ionic conductivity which arises from the mobility of the ions is a very important property of a group of ionic compounds. It is the charged ionic point defects. Charged ionic point defects. We have talked about ionic point defects as well as electronic point defects. Here it is the charged ionic point defects which are primarily responsible for this property. So, once again it is related to the point defects, no doubt, but they are the defect compensation is by ionic defects, they are more predominant defects in these oxides than the electronic defects, and the stoichiometry, the extent of stoichiometry is very limited, is extremely limited. There exists a strong correlation between the charge and mass transport and therefore ionic conductivity and diffusion coefficient. So, that is also another point of our interest. Now, if a ion is moving in a through a lattice, we can consider a kind of energy or the variation of energy based on its particular site where it is located. So, as a function of distance, one can plot this kind of potential wells or potential barriers. So, these are basically the interatomic spacing, and the ions is moving through the surroundings of another set of ions. So, as in any other diffusion mechanism and so on, it has to go through a barrier. It has to go through a barrier and then comes down a low energy sites and a high energy sites. So, periodically it moves like that. Now, this is what happens, they are basically symmetrical whenever there is no electrical field. If there is an electrical field of let us say E and at a with a distance of interparticle distance of A, so the force experienced by that particle is an ionic charge, of course, the ionic species. So, in the application in the when an electric field is applied, a force is getting experienced and that force is actually this one, okay. And there is a depression, and there is a depression of the energy in this direction. So, the there is a less potential on this side than the higher potential on this side. Naturally, there is a driving force which will drive these ions towards the application of the electric field. So, this is the basic thing, and the energy barrier here is delta G star, both in this case as well as in this case. So, this has only been depressed in this direction. The energy barrier to the migration of charged species, that is what we have considered. If the situation is like that, we can consider the migration of the ion, coming back to that, migration of the ion in the forward direction, and there is a finite possibility the ions can also move back. So, we just consider the two equations, Arrhenius type of equations. So, the flux of the ith species, the number of ions moving forward per unit area, that is the forward direction flux, and that is can be expressed as Z I. These expressions have already been considered earlier. This Z I is the number of charge carrier, number of charges per each charge carrier. E is the electronic charge, Ni is the concentration of that charge of the charge species, A is the distance, that is the interatomic spacing, nu is the frequency, natural vibration frequency of vibration of the atoms, and exponential term what is the minus delta G star the without field, and then plus this is the additional energy change. So, we are talking about this value, okay, and compared to this value, and of course, by k T. So, it is a normal Arrhenius kind of equation, and if it is in the backward direction. So, this is reduced, this is increased actually, the total value is this is a less value than delta G, and this is a higher value, this activation barrier is higher than the delta G. So, less number of ions will be moving forward backward than the forward. So, there will be a forward movement of that. So, the Jnet, the net flux will be forward minus backward, and if you do that, it is sin hyperbolic this, and this is almost equal to 1. So, the ultimately this Jnet will be simplified in this form, okay, 2 Ni E Z I A nu Z I E A E by 2 k T exponential. So, there is this is a constant term, of course, it is dependent on temperature, inversely proportional temperature, and there is a exponential term here. Ultimately, sorry, this can be written as, this is actually sigma I by E according to the definition of the flux density. This is actually sigma I E, and the E term is already there from the earlier consideration, the E is already there. So, there is a E here. So, this can be written, E can be separated out, and this will be actually the sigma, okay, that is the ionic conductivity, because you have considered the movement of the charge species. This is the flux density of the charge density, charge moving per unit time per unit cross section. So, that becomes the charge current density, and this becomes your sigma current density according to Ohm's law. The current density is proportional to the applied field. So, if you take the proportionality constant, that becomes sigma. That is what has been written. I means the ith species, particularly the ith species for which the current density has been, or the flux density has been calculated. Now, this also gives you another relationship, because sigma is actually any mu, okay, the concentration, the charge, and the multiplied by the mobility term. So, one can write mu I, again the mobility of the charge species is also a exponential term. Mobility of the charge species, the sigma is an exponential term, and the mobility is also an exponential term, which is actually delta G star by k T, and this is a pre-exponential constant, where E is there, Z I is there, A is also there, and the nu, the vibrational frequency. Now, this gives a relationship that mu I by E Z I, mu I by E Z I is actually a B I, a mobility of the diffusion coefficient, okay, or the mass transport mobility. So, that becomes this one, and ultimately one can write d I by k T. Okay. So, this is mobility and this is d I. So, the mobility is actually the mobility of the charge carrier is proportional to the d I, the diffusion coefficient, which can be measured maybe independently, because diffusion coefficient also have a very similar mechanism by which the mass transport is taking place. Here the mass as well as charge, only thing the mass is having a charge. The diffusion coefficient, when you measure, it may have the species may have a charge, may not have a charge, but even then we will have a diffusion coefficient. For example, in metals there is no charge, but the diffusion coefficient is there because of the concentration gradient. So, in diffusion coefficient it is the concentration gradient which is basically the driving force, whereas in ionic conductivity it is the impressed EMF, impressed voltage or the impressed field, electric field, which is the driving force, because the species are here charged and therefore, they respond to the electric field as well. So, but since the species are itself contains some mass, so the concentration gradient also plays an important role. So, there is a correlation between the impressed field and the concentration gradient. So, both of them actually drive a charged species into the lattice through the lattice, and this relationship between the movement of the charged species and the diffusion coefficient is known as the Nernst-Einstein relationship. It is an important relationship in ionic conductivity and diffusion, of course. So, both ionic conductivity and diffusion are thermally activated processes, and they are related by this relationship. Now, this is a basically a justification or of this relationship. That means, in reality actually we do get a correlationship between the ionic conductivity and diffusion. This is in case of a CSZ, that is the calcium stabilized zirconia. The diffusion coefficient of oxygen, particularly in this case we have seen earlier that addition of calcium oxide to zirconia creates considerable amount of oxygen vacancy, and that oxygen vacancy favors the movement of the oxygen ions in this lattice, and in fact CSZ is a very good oxygen ion conductor, and one uses it extensively in for different purposes, including sensor applications, oxygen sensor application, and also in high temperature fuel cells. Those things will be discussed later. So, CSZ, calcium stabilized zirconia, is a good oxygen ion conductor, and here what has been plotted is the diffusion coefficient measured by two different techniques. One is direct, maybe a tracer diffusion coefficient measurement. So, where the conductivity is not coming into picture, and in another way from conductivity measurement also one can determine the diffusivity using the Nernst-Einstein relationship. So, this solid line has been plotted based on the conductivity data, whereas these experimental points have been measured by direct measurement of diffusion coefficient without application of electric field. So, by a concentration gradient one can measure the conductivity. So, it has been found, it is as you can see here, that they are very good agreement with each other, both the conductivity data and the direct diffusion measurement, they are good agreement, and that also shows that the diffusion and the validity of the Nernst-Einstein relationship. That means, the conductivity and ionic the diffusion coefficient and ionic conductivity are very, very closely related. Well, if you go little further in the same equations, you will find that ultimately the sigma I is any mu. We have seen earlier the temperature dependence of mu. Here the temperature dependence of overall sigma, same thing is there. Mu is related to di, the diffusion coefficient, and then factor f has been added here. It is not 1, it is different. So, sigma I is actually inversely proportional to temperature in addition to mu. That means, we have di, the diffusion coefficient is an exponential term of temperature or with an activation barrier. In addition, sigma I is inverse if this is taken as constant, although it is not a constant, but there is a in the denominator also the T term is there. So, that is an important consequence and important points to be noted, that the sigma I is also has in the denominator, in addition to the exponential term, also as a T term, and the factor F is depending on the crystal structure and the particular atomistic mechanism of diffusion. Well, there are different mechanisms of diffusion in any system. It may be a vacancy diffusion, it may be an interstitial diffusion, it may be interstitial C diffusion. There are different mechanisms of diffusion. So, atomistic mechanism. So, depending on that, the factor will vary, and also on the crystal structure. For it, for example, it should be, for example, where we are here, no? Yeah. For example, its value, the F value of F, its value is 4 for vacancy mechanism in a sodium chloride structure. If you have a rock salt structure or sodium chloride structure in which the diffusion is taking place by a vacancy mechanism, its value is 4. The temperature dependence the temperature dependence of ionic conductivity generally expressed as, from this it has been simplified like this. Okay. So, sigma I T, sigma 0 exponential minus delta G by K T, taking all the exponential terms together, but the most important thing is it is normally expressed as sigma I T, it is multiplied by T, and then only a log plot, log sigma T, sigma I T, sigma 0 and 1 by T, not log plot, the Arrhenius plot, but there one should take not sigma I only or sigma only, but sigma T, that is that then only we get a straight line. So, this is not true for electronic conductivity or semiconductors. See, in semiconductors we plot only sigma, log sigma, whereas in ionic conductors one need to plot this sigma T to get a straight line or to get the value of delta G. Now, there is something else to also, mu I, the mobility, we have already seen this. It can be again expressed as mu I 0 by T exponential k T. So, this is also mu I also has a in the denominator you have a T, but more important is here we are trying to concentrate on this term. Delta H m is the enthalpy of migration of the ion or the ionic defect. Okay. So, this delta G now may have two different components. One is called the migration, that is actual mobility, migration of the defect, but as the defect formation is also thermally activated process, the activation energy for the intrinsic ionic conductivity includes the enthalpy changes for both formation and migration of the defects. So, when we are talking about sigma T, this is only for the migration, the mobility term, but if you are talking about the concentration of the defects, how many ions are actually taking part in the process, that depends on the how many defects are there. Particularly we are talking about the defect, the vacancy mechanism of diffusion, then you will find first of all the vacancy have to be created either thermally activated or by some extrinsic manner by adding some impurities and so on. For example, in calcium stabilized zirconia, by adding calcium oxide we are creating defects, we are creating oxygen vacancies, and that oxygen vacancy concentration is proportional to the amount of calcium you are adding. It is not dependent on temperature. Okay. However, in some other cases when the impurity effect is not there, the intrinsic defects are created by temperature rise, and therefore, that defect concentration is proportional or is dependent on the activation energy of that particular process, which we have seen earlier in case of point defects. So, point defect creation needs some activation energy, its migration also needs activation energy, and these are the two terms which has been given here, sigma T. So, it is a formation defect or the activation energy for the formation of the defects and the activation energy for the migration of defects. So, the overall activation energy consists of two different terms, one is the formation of the defect, another is for the migration of the defect. By some means, if the formation is already there, so the temperature will not be needed for the formation, then only the migration will be effective. So, formation energy is not required, but generally it will have two different terms. Well, with this background, I think what I will do, I will go, I think this I will discuss first and then go back. These are the activation energies for the formation and migration of ionic defects. So, if you plot log sigma t as a function of 1 by t, that is the normal Arrhenius plot kind of thing, then once again you have two different activation energies. At the lower temperature it is only delta H m, because you are not generating any defect here. Okay. The defects have already been generated if they are at a high temperature, and whatever migration, because this energy is not sufficient for creation of the intrinsic defect. This at this temperature it may be impurity effect which becomes predominant, which we have seen earlier in impurity controlled semiconductor also. So, same thing can happen. So, if you have already introduced some defect by solid solution effect or impurity effect, then those defects or those active sites, active charge carriers will migrate at the low temperature, and the only energy to be supplied is delta H m. However, at higher temperature you need both the terms to be supplied, both the terms. Here of course, R has been written, this is as per mole. If you can also use K because if it is per number of charge carriers. Okay. So, delta H f is the additional energy you need to create the vacancy at high temperature. So, you have a lower activation energy here and a higher activation energy there, a steeper slope there and a lower shallower slope here. So, from these two regions also one can be identified, this is a kind of extrinsic region, this is an intrinsic region. So, just like as in semiconductors, you can also have in ionic conductivity two regions, one is the extrinsic region, another is the intrinsic region. Now, I think this I have already discussed. This is the conductivity versus temperature plots of a few highly conducting ionic conductors. There is a plots of some compounds, not all of them are oxides, because oxides are not only the ionic conductors, there are many non-oxides, particularly the alkali halides like this, sodium silver iodide. In fact, silver iodide is one of the very important ionic conductors, in which all the conductivity is because of the silver ion and not the iodine ion. So, it is a cationic conductor. All these are basically cationic conductors. Okay. So, and there is a phase transformation around 150 degrees or so. So, it is a very sudden change of phase transformation. The higher phase, the higher polymorphic form has a much higher conductivity than the lower polymorphic from lower temperature polymorphic form. And as you can see, the conductivity has been plotted here as a sigma t. So, to get the straight line behavior, you have to plot sigma t and just not only sigma. So, silver iodide is one of the compounds having a very high ionic conductivity. You have also silver rubidium iodide. Okay. Silver, a part of the silver has been replaced by rubidium, and that increases the defect concentration, and even at the room temperature, even at the not only at room temperature, but also at the lower temperature. So, this transformation has been avoided. Okay. So, this transformation has been stabilized, and even at room temperature you can get a very high ionic conductivity, which is very high compared to many other oxides. There is another compound, silver aluminum oxide. In fact, it is what we call silver beta alumina. Okay. Beta alumina is a compound which is a layered structure, and in which one of the layer is a very disordered layer, and these cations are placed in this disordered layer, either silver or sodium, lithium. All these alkali metal ions can be placed or are located in this disordered structure. So, at a very low temperature, very close to room temperature, within 100-150 degrees, you have a very high conductivity of cations. And once again, silver beta alumina or lithium sodium beta alumina in particular has a lot of industrial applications. Once again, as one can generate power out of this, one can make batteries, sodium sulfur batteries, making use of these compounds as they are oxides again, but having a very high conductivity comparable to these halides. Okay. And at a very low temperature, fairly low temperature, 150 degrees, they can be very highly conducting and can be used effectively as an electrolyte in some of the battery systems, high temperature battery systems. You have silver bromide, silver chloride, their conductivities are slightly low, and then you have a host of calcium halides like calcium chloride, calcium bromide, calcium iodide, all of them do have calcium conductivity, calcium ion conductivity. And the only example in this figure of an ionic conductor is zirconia calcea, which have been mentioned earlier, zirconia calcea stabilized zirconia, but we will see later on that other stabilizers like yttrium oxide, scandium oxide, etc., also have a very good oxygen ion conductor, and the conductivities are comparatively higher compared to this calcium stabilized zirconia. And in fact, in sensors, in sensor application and fuel cells, we will see that it is the zirconia yttria system is more preferred than zirconia calcea, and in some cases zirconia scandia Sc2O3 is also added, and the conductivity is in fact much higher, although it is little costly, and so for economic reasons it is not used that much, but zirconia yttria is one of the almost commercial material which is extensively used as a oxygen ion conductor in addition to its other properties. Few more oxides also have a oxygen ion conductivity like cerium oxide, thorium oxide. So, all of them have cubic fluoride structure, and you can have fairly good amount of oxygen ion conductivity. As you have seen from the concentration versus PO2 diagram, Of course, in these not much of investigation has been made so far as the partial pressure dependence of either the silver or rubidium and all that, because these are mostly solid, you do not get vapors out of that so easily. Whereas, when you talk about oxides, one of the constituents, the oxygen, is available in the form of a gaseous substance, and it is available in atmosphere. So, oxygen partial pressure dependence on these are quite important, and it does not it is not true that all oxygen partial pressures the oxygen ion conductivity will be available. Only in certain oxygen partial pressure range, the so called intermediate oxygen partial pressure range, where the oxygen ion conductivity will be predominant, but if the oxygen partial pressure is either too high or too low, the defect situation, the defect compensation changes, and one can get again the semiconductivity in those. It tends to become a non-stoichiometric oxides, and the semiconductivity creeps in. That when the semiconductivity comes in, of course, the material will not be useful as a solid electrolyte, but maybe it can be used for some other purposes. Well, we are talking about only about the cations like alkali metals or the oxygen ion conductors, but there are ionic compounds or ionic conductors in which even the proton, even the hydrogen ion, not the proton, the hydrogen ion can conduct. There are oxides, we will see some of the examples later on, where even the hydrogen ion can be a mobile species. Okay. So, of course, the mechanism is slightly different there, the origin of this hydrogen ion is a little different, but it is possible to have hydrogen ion conductivity in some of the oxides. Now, when you are talking about the ionic conductivity, one more important parameter we have to always consider, and that we have talked about earlier, that is what is called the transference number. Transference number is a very important parameter in relation to the oxygen the ionic conductivity, and here is a list of the transference number of some of the compounds have been mentioned, which have been mentioned earlier at different temperatures, and the columns are cation conductivity, anion conductivity, and the electron or hole conductivity. Okay. These will be not capital T, sorry, just a minute. Okay. So, coming back to the table, these are the typical transference numbers of a few ionic compounds. To start with sodium chloride, Roxel structure, as you know, there is a sodium ion diffusion, there is sodium ion diffusion, considerable sodium ion diffusion, and the cation diffusion is maximum. Anion, there is hardly any, except at slightly higher temperature, that means some chlorine ion can diffuse at a higher temperature like 600 degrees, close to its melting point, and then there is of course no electronic diffusion, electronic conductivity or electron transport at all. So, this is purely ionic conductors. So, is the case with potassium chloride. As you can see, it is the potassium ion which moves cation conductors, and at higher temperature some amount of anionic conductivity also come in. Here still very little of anionic conductivity is there. Silver chloride, there is no anionic conductivity, fully cationic conductors from 20 to almost 350 degrees. Silver bromide, same thing, again cationic conductor, 100% cationic conductor. Barium fluoride or lead fluoride, these are the fluorides which have no cationic conductivity, but fluorine ion conductivity. Okay. fluorine ion conductivity is there, but one thing you must know, calcium fluoride, CaF2, that is the fluoride structure from which the name fluoride structure has come, there that is absolutely an insulating material. Okay. But barium fluoride and lead fluoride has a good fluorine ion conductivity. Iron oxide, as you have discussed on several occasions, that it is a semiconducting oxide with cation vacancy, and so there is hardly any cationic conductor, 10 to the minus 4 is very small. So, the transparent number of the cations, but the electronic, in fact, is a whole conductor. The whole conductivity is almost full in the sense purely whole conductor, there is no cationic conductor. This we have discussed again, zirconia, calcium stabilized zirconia. Above, of course, the conductivity is appreciable only above about 600 degrees centigrade or so. At below 600, it is purely almost for all practical purposes, it is a insulator. The mobility is extremely low. So, only above 600 or 700 degrees, you have appreciable amount of oxygen and conductivity, and as you can see, there is hardly any electronic or hole conductivity, whereas it is 100% T ion is 1, T anion is 1, that means oxygen and conductivity. We have mentioned about silver beta alumina, this is sodium beta alumina, same thing, silver has been replaced by sodium, otherwise everything remains same, the structure and the formula also is same. This is less than 800 degrees. Okay. In fact, even at 150 degrees they have a very good conductivity, and this is sodium ion. Okay. I am sorry, once again there is some problem. This is sodium ion, and once again you have very low electronic conductivity or hole conductivity. Almost everything is because of this sodium ion conductivity, because sodium ion has been mentioned because there are two different cations. Okay. Aluminum is not the conductor. If you talk about just a reference, just a comparison, if you talk about glass, normal soda lime silica glass, there also you have 100% conductivity because of the sodium ion. Of course, it is actually used as a solid electrolyte in pH meters. Okay. So, that is the reason it has been listed here. And finally, you have a glass, another glass composition just for comparison, having some iron oxide FeO, Fe2O3, that is kind of a system, and this is a purely electronic conductor, almost like pure electronic conductor, except there is very little of calcium oxide conductivity. So, what we can, why these two glasses have been mentioned here, that by just changing the composition, the glass, basic glass can be changed from an ionic conductor to an electronic conductor, and the conductor's conductivity is primarily because of the presence of the semiconducting oxides, right. So, that more or less completes our discussion on ionic conductivity and also the electrical conduction in oxides or ceramic materials. To just summarize, we have discussed the various concepts of conduction mechanisms and the basic parameters, basic theories to explain the conductivity of different solids, whether it is metals, whether it is elemental semiconductors or some of the insulators. And when you are talking about oxides, we have all possibilities. We have insulators, we have semiconductors, we have even conductors in some of the oxides, which we have not discussed that much in details, but it very much there. There is some metal insulator transitions, and in addition, particularly in ceramics, we have a range of solid electrolytes or ionic conductors, which are also of very much technological importance, and their mechanisms we have discussed, their temperature dependence we have discussed, but one important thing for oxides is the partial pressure dependence. The atmosphere has a very important role to play so far as the charge carrier concentration is concerned, and of course, the temperature has a very important effect. In most cases it is exponentially dependent, and in case of ionic conductivity we have a temperature term also in the denominator, and that makes the situation slightly different, but in general it is exponentially dependent on temperature. So, that completes our discussion on the electrical conduction in ceramic materials. Later on we will see how the insulators, because many of the oxides or many of the ceramic materials are actually insulators. So, how they respond to the electric field, whether it is the dielectric material, piezoelectric material or the pyroelectric material. With this we come to the end of this particular module. Thank you for your patience hearing.